In the great expanse of the solar system, where the sun's light grows feeble and the darkness deepens, there exists a world that has become the punchline of astronomy classes and the subject of countless juvenile jokes. It orbits nearly 3 billion kilometers from the warmth of our star, a distance so vast that sunlight takes almost 3 hours to reach its cloud tops. This is Uranus, the seventh planet from the Sun, and for reasons that have nothing to do with science and everything to do with the accidental pronunciation of its name, it has never quite received the respect it deserves. But beneath this superficial ridicule lies one of the most extraordinary and least understood objects in our cosmic neighborhood, a world of sideways seasons, diamond rains, and magnetic fields so strangely oriented that they defy everything planetary scientists thought they understood about how worlds generate their invisible shields. For nearly 4 decades, humanity's entire close-up knowledge of this enigmatic planet has rested upon a single fleeting encounter, a brief handful of hours in January 1986, when a solitary robotic spacecraft, Voyager 2, hurtled past at tremendous speed, capturing images and data that have formed the foundation of every textbook, every documentary, every scientific paper about Uranus ever since. It was the most ambitious planetary flyby ever attempted, a technological triumph that revealed a world of serene blue-green beauty, but it was also merely a glimpse, a snapshot taken in haste as the spacecraft continued its grand tour toward the outer darkness. In the years that followed, Uranus receded from the public imagination, overshadowed by the dramatic storms of Jupiter, the magnificent rings of Saturn, and the violent winds of Neptune. It became the forgotten planet, the one that schoolchildren struggled to remember, the one that seemed to offer nothing but cold stillness in the depths of space. But while the world looked away, scientists have been quietly working, re-examining old data with new eyes, developing sophisticated computer models that simulate conditions no spacecraft has ever measured directly, and pointing the most advanced telescopes ever built toward that distant point of blue-green light. What they have found is nothing short of revolutionary. Uranus, it turns out, is not the static, featureless world that Voyager 2 seemed to reveal. It is a place of tremendous storms, of seasonal changes so extreme that they reshape its entire atmosphere, of internal processes so poorly understood that they challenge our most fundamental assumptions about how planets form and evolve. The story of Uranus is being rewritten in real time, and it is a story that speaks to something deeper than planetary science. It speaks to the nature of knowledge itself, to the way that human understanding advances not in steady increments, but in sudden leaps, not through comfortable certainties, but through the gradual accumulation of evidence that eventually forces us to abandon everything we thought we knew. This is a documentary about that process of rediscovery, about the strange sideways world that has captivated a new generation of astronomers, and about the profound questions that remain unanswered as we stand on the threshold of what may be the next great chapter in planetary exploration. It is a story that begins in a back garden in England in the 18th century, that passes through the golden age of robotic spaceflight in the 20th, and that now, in the 21st century, arrives at a moment of extraordinary possibility, a moment when the scientific community has declared, with unprecedented clarity, that returning to Uranus must be humanity's highest priority in planetary science. The launch window is opening. The planetary alignment is perfect, and the technology exists to send an orbiter that could spend years studying this world rather than mere hours. The question is whether we will seize this opportunity, whether we will commit the resources and the political will necessary to finally understand this strange and wonderful planet. But even as we contemplate that future, we must first understand what we have already learned, how the patient work of observation and analysis has transformed our picture of Uranus, and why the discoveries of recent years have made the case for a return mission so compelling that it can no longer be ignored. This is the story of Uranus, the planet that rolls around the Sun on its side, the planet with the coldest atmosphere in the solar system. The planet whose magnetic field is so strangely offset that it creates auroras that dance across entirely the wrong parts of the sky. The planet whose interior may be composed of materials so compressed that carbon atoms are squeezed into diamonds that rain downward through layers of supersonic water and ammonia. It is a story of violence and tranquility, of ancient collisions and present-day mysteries, of moons that may harbor hidden oceans and rings made of the darkest material in the solar system. And it is a story that is still being written, with new chapters added almost monthly as telescopes improve and as theoretical models grow more sophisticated. By the time this documentary reaches its conclusion, you will understand why Uranus has captured the imagination of a new generation of planetary scientists. Why the jokes that once seemed so clever now feel so inadequate, and why the next decade may finally give this forgotten world the attention it has always deserved. But before we can look forward to the missions that may soon depart for this distant realm, we must first look backward to the very beginning, to the moment when a musician and amateur astronomer named William Herschel pointed a homemade telescope at the night sky and changed humanity's understanding of the solar system forever. It was the 13th of March in the year 1781, and the city of Bath in England had settled into the quiet routines of evening. William Herschel, a German-born musician who had found success as an organist and composer in his adopted country, stood in the garden behind his house on New King Street, peering through a telescope of his own construction. He was engaged in a systematic survey of the night sky, a methodical examination of the stars that would eventually lead him to catalogue thousands of celestial objects. On this particular night, his attention was drawn to an object in the constellation of Gemini, a faint disk that appeared slightly different from the fixed stars surrounding it. Herschel was not the first human being to see this object. Indeed, it had been observed many times before by astronomers who had simply recorded it as another star, but he was the first to notice that it moved. Over subsequent nights, he tracked its slow progress against the background of fixed stars, and he came to a conclusion that would rock the astronomical world. He had discovered a new planet, the first planet to be found in recorded human history that had not been known to the ancient civilizations who named the 5 visible worlds: Mercury, Venus, Mars, Jupiter, and Saturn. Herschel initially believed he had found a comet, and he reported it as such to the Royal Society, but as other astronomers around Europe turned their telescopes toward this strange object, they gradually realized its true nature. It orbited the Sun at twice the distance of Saturn. It displayed a visible disk when viewed at high magnification, and its motion was precisely what would be expected of a planet following Kepler's laws. Within 2 years, the astronomical community had reached a consensus. This was indeed a new planet, and it doubled the known size of the solar system overnight. Herschel, ever the showman, wanted to name it Georgium Sidus, the Star of George, in honor of his patron, King George III. This suggestion was not well received outside of England, and for decades the planet was referred to by various names, including Herschel itself, in honor of its discoverer. Eventually, the astronomical community settled on a compromise following the tradition of naming planets after classical deities. They chose Uranus, the father of Saturn and the grandfather of Jupiter in Roman mythology. It was an appropriate name for a planet that orbited beyond Saturn, continuing the generational pattern that had begun with the innermost worlds. But Herschel's discovery was more than just an addition to the catalogue of planets. It fundamentally altered humanity's conception of the solar system. For millennia, thinkers had assumed that the 7 celestial bodies visible to the naked eye, the Sun, the Moon, and the 5 classical planets, represented the complete architecture of our cosmic neighborhood. The discovery of Uranus demonstrated that this assumption was false, that there might be more worlds waiting to be found, that the solar system was larger and more complex than anyone had imagined. This realization would eventually lead to the discovery of Neptune, to the identification of the asteroid belt, to the recognition that the solar system extends far beyond the orbit of the outermost planets into a vast realm of icy bodies known as the Kuiper belt. But for nearly 2 centuries after Herschel's discovery, Uranus remained a mystery. Astronomers could measure its orbit, they could observe its faint disk, they could note its unusual greenish color, but they could learn little else. The telescopes of the 18th and 19th centuries were simply not powerful enough to resolve details on a world so distant. Even the largest observatories could show only a featureless disk, a tiny circle of pale light that revealed nothing of the storms and clouds that might rage within its atmosphere. It was not until the 20th century that technology began to catch up with curiosity. Spectroscopic analysis revealed the presence of hydrogen, helium, and methane in Uranus's atmosphere. The methane explaining the planet's distinctive color by absorbing red light and reflecting blue and green. Careful observations of the orbits of its 5 known moons, Titania, Oberon, Umbriel, Ariel, and Miranda, allowed astronomers to calculate the planet's mass and to infer something about its internal structure. And in 1977, a remarkable accident occurred that revealed Uranus possessed something no one had suspected. Astronomers observing the planet as it passed in front of a distant star, an event known as an occultation, noticed that the star flickered several times before and after the planet itself blocked its light. The only explanation for this flickering was that something was orbiting Uranus, something that briefly blocked the starlight. Further analysis confirmed the discovery. Uranus had rings. It was the first time rings had been detected around any planet other than Saturn, and it suggested that ring systems might be more common than previously thought. By the time the 1980s arrived, scientists knew enough about Uranus to recognize that it was fundamentally different from the gas giants Jupiter and Saturn. It was smaller, denser, and colder, and its composition seemed to include a much higher proportion of elements heavier than hydrogen and helium. The term ice giant was coined to describe this new class of planet, distinct from the gas giants that had dominated the outer solar system. But the details remained frustratingly out of reach. What was the interior structure of Uranus? What drove its weather, if anything did? Why was its axis tilted to such an extreme degree? How many moons did it actually have, and what were they like? These questions would remain unanswered until humanity could send a spacecraft to this distant world, a mission that would require technological capabilities far beyond anything that had been attempted before. And then, in the summer of 1977, just as the rings of Uranus were being discovered, such a mission was already in the planning stages. Two spacecraft, Voyager 1 and Voyager 2, were being built for a grand tour of the outer solar system, a once-in-a-lifetime opportunity that took advantage of a rare alignment of the outer planets that occurs only once every 175 years. The mission planners at NASA's Jet Propulsion Laboratory had designed a trajectory that would allow Voyager 2, if all went well, to visit Jupiter, Saturn, Uranus, and Neptune in succession. It was an audacious plan, a journey that would take more than a decade and would require the spacecraft to operate flawlessly for years beyond its original design lifetime. But if it succeeded, it would transform humanity's understanding of the outer solar system forever. And succeed it did, though not without challenges and compromises along the way. The journey of Voyager 2 to Uranus was a testament to human ingenuity and perseverance. Launched from Cape Canaveral on August 20, 1977, 16 days before its twin, Voyager 1, the spacecraft embarked on a trajectory that would take it first to Jupiter, then to Saturn, and then onward to the ice giants beyond. The Saturn encounter in 1981 was particularly critical because it included a gravitational assist that would bend Voyager 2's trajectory precisely enough to reach Uranus. Any error in the navigation, any deviation from the planned course, and the spacecraft would miss its target by millions of kilometers, never to have another chance. The navigators at JPL calculated the required trajectory with exquisite precision, and Voyager 2 performed flawlessly, emerging from the Saturn system on a course that would bring it to Uranus 4.5 years later. Those 4.5 years were not idle. The spacecraft continued to send back data from the depths of the solar system, measuring the solar wind, the magnetic field, and the cosmic ray environment far beyond the orbit of Saturn. But as the encountered date approached, the mission team began the intense preparations that would be necessary to extract the maximum science from this brief flyby. Uranus was so distant that even at Voyager 2's approach speed of more than 50,000 miles per hour, the encounter would last only a few hours. In that time, the spacecraft's instruments would have to capture everything: images of the planet and its moons, measurements of its magnetic field, analysis of its atmospheric composition, characterization of its rings. There would be no second chances, no opportunity to go back and observe something that was missed. The spacecraft's systems, now nearly 9 years old, would have to perform perfectly. The radio signal, traveling at the speed of light, would take 2 hours and 45 minutes to reach Earth from Uranus, meaning that no real-time control was possible. The spacecraft would have to execute its pre-programmed sequence of observations autonomously, trusting that its onboard computers would make the right decisions at the right moments. On January 24, 1986, after more than 8 years of flight, Voyager 2 arrived at Uranus. The encounter was a triumph of engineering and science. The spacecraft flew within 81,000 kilometers of the planet's cloud tops, closer than it had come to either Jupiter or Saturn, and its instruments returned a wealth of data that would keep scientists busy for decades. The images revealed a world of surprising blandness, at least in visible light. Where Jupiter displayed bands of color and the Great Red Spot, Where Saturn showed subtle shading and occasional storms, Uranus presented a featureless blue-green disk, almost completely devoid of contrast. It was as if the planet were wrapped in a uniform haze that obscured any atmospheric activity beneath. But other instruments told a different story. The magnetometer revealed that Uranus possessed a magnetic field, but one unlike any ever measured. Instead of being roughly aligned with the planet's rotational axis, as is the case for Earth, Jupiter and Saturn, the Uranian magnetic field was tilted by nearly 60 degrees and offset from the planet's center by a third of its radius. It was as if the planet's magnetic generator were located not in its core, but somewhere in its outer layers, producing a field that wobbled through space as the planet rotated. The ultraviolet spectrometer detected emissions that indicated the presence of auroras, but these auroras did not occur at the poles as they do on Earth. Instead, they appeared at mid-latitudes, tracing the complex geometry of the tilted magnetic field. The radio science experiment measured the planet's atmosphere, revealing temperatures that were surprisingly uniform from pole to equator and winds that blew in the direction of the planet's rotation at speeds of up to 500 miles per hour. And the imaging system, despite the bland appearance of the planet itself, returned stunning pictures of Uranus's 5 largest moons, revealing worlds of incredible diversity and complexity. Miranda, the innermost of the major moons, was perhaps the most surprising. Its surface showed a patchwork of different terrains, some ancient and heavily cratered, others young and grooved with tectonic features, as if the moon had been shattered and reassembled multiple times over its history. Ariel displayed evidence of past volcanic activity, though the volcanoes had erupted not molten rock but liquid water and ammonia that had frozen solid in the extreme cold. Umbriel was dark and ancient, its surface uniformly covered with impact craters. Titania and Oberon, the 2 largest moons, showed both cratered highlands and younger plains, suggesting complex geological histories. The rings of Uranus, discovered accidentally 9 years earlier, were imaged directly for the first time. They proved to be dark and narrow, composed of material so black that it reflected less than 2% of the sunlight that struck it. 11 distinct rings were identified, along with evidence of shepherd moons that helped maintain their structure. And the spacecraft discovered 10 new moons, bringing the total known to 15 and revealing that Uranus possessed a complex system of small bodies orbiting within and beyond its rings. But perhaps the most puzzling finding from the Voyager 2 encounter was the temperature of Uranus's atmosphere. The spacecraft measured the temperature at the cloud tops and found it to be minus 224 degrees Celsius, making Uranus colder than Neptune despite being closer to the Sun. This was deeply puzzling. Neptune, farther from the Sun, should have been colder, yet it was not. Something was preventing Uranus from radiating the internal heat that should have been left over from its formation, and that something remained a mystery for decades. When the last data from the Uranus encounter had been transmitted back to Earth, when the spacecraft had been reoriented for its onward journey to Neptune, the scientists and engineers at JPL could reflect on a mission that had exceeded all expectations. They had revealed a world that was simultaneously bland and bizarre, a planet whose serene exterior concealed a wildly asymmetric magnetic field, a system of dark rings, and a family of moons with violent geological pasts. They had answered many questions, but they had raised many more. And then, for nearly 40 years, no other spacecraft would visit Uranus. The Voyager 2 encounter became the foundation of all knowledge about this distant world, a single data point in time that scientists would analyze and reanalyze, searching for insights that had been missed in the first pass. The spacecraft itself continued on its journey, passing Neptune in 1989 and then heading out of the solar system entirely. But Uranus receded into the background of planetary science, overshadowed by more accessible targets and more pressing priorities. It would take decades and the development of new technologies and new analytical techniques for Uranus to return to the forefront of scientific attention. And when it did, the revelations would come not from a new spacecraft, but from old data reinterpreted with fresh eyes, and from telescopes on and around Earth that could observe the distant planet in ways that Voyager 2 never could. The years following the Voyager 2 encounter were a period of consolidation rather than discovery for Uranus. Scientists pored over the data returned by the spacecraft, publishing hundreds of papers that analyzed every aspect of the Uranian system. They mapped the geology of the moons in exquisite detail. They modeled the structure of the rings. They developed theories to explain the tilted magnetic field and the cold atmosphere. But without new data, progress was necessarily limited. The Voyager 2 flyby had lasted only a few hours, and the spacecraft's instruments had captured only a snapshot of the Uranian system at a single moment in time. What was needed was sustained observation, the kind of long-term monitoring that could reveal how Uranus changed over days, months, and years. This was impossible with spacecraft, but it was increasingly possible with telescopes. Throughout the 1990s and 2000s, astronomers used the Hubble Space Telescope, the Keck Observatory in Hawaii, and other advanced facilities to observe Uranus whenever its position in the sky allowed. These observations were challenging. Uranus is small and distant, and even the best telescopes struggled to resolve details on its disk. But patience and technique gradually yielded results. In 1997, Hubble observed a bright cloud feature in Uranus's southern hemisphere, the first definitive evidence that the planet's atmosphere was not as static as Voyager 2 had suggested. Over the following years, more clouds were observed, appearing and disappearing in patterns that seemed to correlate with the planet's seasons. The Hubble observations, spanning more than 2 decades, revealed that Uranus's atmosphere becomes more active as the planet approaches equinox, the time when the Sun is directly over the equator. During these periods, bright clouds appear at mid-latitudes, and the overall circulation of the atmosphere seems to intensify. As the planet moves toward solstice, when one pole points toward the Sun, activity shifts toward that pole and a thick cap of haze builds up in the polar region. These seasonal changes are the most extreme in the solar system, a direct consequence of Uranus's extraordinary axial tilt. While Earth's seasons are caused by a tilt of 23.5 degrees, producing moderate variations in sunlight between summer and winter, Uranus's tilt of 98 degrees means that each pole experiences 42 years of continuous sunlight, followed by 42 years of continuous darkness. During the long polar day, the Sun climbs to a maximum altitude of 98 degrees above the horizon, actually passing through the zenith and continuing around the sky in a circular path. During the long polar night, the Sun never rises at all, and the pole is plunged into darkness for more than 4 decades. These extreme conditions drive atmospheric circulation patterns that have no analogue on any other planet. But the seasonal changes observed by Hubble were just the beginning. In the 2010s, a series of observations using the Keck Observatory's adaptive optics system revealed something even more dramatic. Uranus was experiencing massive storms, the largest ever seen on the planet. In 2014, Keck images showed 8 bright cloud features in Uranus's northern hemisphere, some of them so large that they accounted for 30% of all the light reflected by the planet at certain wavelengths. These storms were not the transient features that had been observed before. They persisted for months and evolved in complex ways, sometimes merging with each other, sometimes spawning smaller cloud features that drifted away on atmospheric currents. Amateur astronomers, armed with increasingly sophisticated equipment, were able to observe these storms from their backyard observatories, contributing to a global effort to understand Uranian meteorology. The storms raised profound questions about the nature of Uranus's atmosphere. On Jupiter and Saturn, storms are driven by internal heat, the slow release of energy left over from the planet's formation. Uranus, by contrast, radiates very little internal heat. Where, then, did the energy for these massive storms come from? One possibility is that they are driven by sunlight, by the seasonal changes in solar heating that occur as Uranus moves through its long year. The fact that the storms appeared as the planet approached northern spring, when the sun was rising higher in the northern sky, supported this idea. But sunlight alone seemed insufficient to power storms of such magnitude. Another possibility is that Uranus does have internal heat, but that it is trapped deep within the planet, released only occasionally when conditions allow. This idea gained support from theoretical modeling, which suggested that the unusual interior structure of Uranus might act as an insulator, preventing heat from escaping except through localized upwellings that manifest as storms. The question of Uranus's internal heat would become one of the central mysteries of the planet, a mystery that recent research has begun to unravel in surprising ways. In 2025, 2 independent studies published within months of each other reported that Uranus does indeed emit more energy than it receives from the Sun, but only about 15% more. This is a tiny fraction compared to Neptune, which emits more than twice as much energy as it receives, and it helps to explain why Uranus is so cold despite being closer to the Sun. But it also raises the question of why Uranus is so different from its twin. The answer, it seems, may lie in Uranus's violent past, in an ancient collision that not only knocked the planet onto its side, but also fundamentally altered its internal structure. Computer simulations published in 2018 by a team at Durham University in England provided the most detailed picture yet of how such a collision might have occurred. The researchers ran more than 50 different impact scenarios, varying the size and composition of the impacting body, the angle of impact, and the speed of collision. They found that the most plausible scenario involved a protoplanet 2 to 3 times the size of Earth, composed primarily of rock and ice, striking a young Uranus a glancing blow. The impact would have lasted only a few hours, but its effects would have been permanent. It tilted Uranus's rotational axis to its current extreme angle. It deposited a large amount of material into the planet's interior, and it created a shell of high-entropy material that acts as an insulator, trapping heat deep within the planet. This insulating layer explains both Uranus's low heat output and its extremely cold upper atmosphere. The heat is there, but it cannot escape. The collision also helps to explain Uranus's bizarre magnetic field. The material deposited by the impact may have created a region in the planet's mantle where convection occurs differently than in the core, generating a magnetic field that is offset and tilted. This is a radically different picture from the one that existed before the simulations, when scientists assumed that Uranus's magnetic field, like those of other planets, originated in a dynamo action at the core. Now it appears that the field may be generated in a shell of material that was added to the planet billions of years after its initial formation. The implications of this idea extend far beyond Uranus itself. If ice giants can have their internal structures fundamentally altered by giant impacts, then our understanding of how planets form and evolve may need revision. The classical model, in which planets accrete from the solar nebula and then slowly differentiate into core, mantle, and atmosphere, may be too simple. In reality, the early solar system was a violent place, full of collisions that could reshape worlds in hours. Uranus bears the scars of that violence to this day, scars that are written in its tilt, its cold atmosphere, and its strangely offset magnetic field. The magnetic field of Uranus is perhaps the most fundamentally bizarre aspect of the entire Uranian system. When Voyager 2 measured it in 1986, the results were so unexpected that many scientists initially suspected an instrument malfunction. The field was tilted by 58.6 degrees relative to the planet's rotational axis, meaning that as Uranus spins, its magnetic field wobbles through space like a top that is about to fall over. Even more strangely, the center of the magnetic field was offset from the planet's geometric center by about a third of Uranus's radius, roughly 8,000 kilometers. This means that the magnetic field is not dipolar in the way that Earth's field is, with field lines emerging from near the South Pole and converging near the North Pole. Instead, the Uranian field is more complex, with multiple poles and a geometry that changes as the planet rotates. The consequences of this strange magnetic geometry are profound. Charged particles trapped in the magnetic field, the particles that create auroras on other planets, follow paths that are wildly different from those on Earth. Instead of spiraling down toward the poles, where they collide with atmospheric gases to create shimmering curtains of light, these particles are directed toward mid-latitudes, producing auroras that appear far from where they should. The Hubble Space Telescope has imaged these Uranian auroras in ultraviolet light, revealing bright emissions that dance across the planet's middle latitudes as the magnetic field wobbles through space. In 2023, astronomers using the Keck telescope in Hawaii detected infrared auroras on Uranus for the first time, after 30 years of searching. These infrared emissions come from molecular hydrogen in the upper atmosphere, excited by collisions with charged particles. They provide a new window into the complex interactions between the solar wind, the magnetic field, and the atmosphere of Uranus, revealing processes that are unlike anything seen elsewhere in the solar system. But the strangeness of Uranus's magnetic field extends beyond its geometry. When Voyager 2 flew past the planet, it measured the size of the magnetosphere, the bubble of space dominated by Uranus's magnetic field, and found it to be surprisingly small. This was puzzling because Uranus is a large planet with a substantial magnetic field, and it should have carved out a sizable cavity in the solar wind. For decades, scientists assumed that the small magnetosphere was simply a characteristic of Uranus, another oddity to add to the list. But a reanalysis of the Voyager 2 data published in 2024 by a team led by Jamie Jasinski at NASA's Jet Propulsion Laboratory, revealed that the original interpretation was wrong. The small magnetosphere measured by Voyager 2 was not typical of Uranus at all. It was the result of a temporary condition, an episode of intense solar wind that had compressed the magnetic field just as the spacecraft happened to be passing through. When Jasinski and his colleagues re-examined the data in the context of solar wind conditions at the time, they realized that Voyager 2 had arrived during a period of unusually high solar wind pressure. The magnetosphere had been squashed, like a balloon squeezed by a giant hand, giving the false impression that it was permanently small. In reality, the Uranian magnetosphere is probably much larger and more dynamic, expanding and contracting in response to changes in the solar wind, just as Earth's magnetosphere does. This reanalysis has profound implications for our understanding of the Uranian system. A larger magnetosphere means more space for plasma processes to operate, more interactions between the magnetic field and the moons and rings, more opportunities for charged particles to be accelerated to high energies. It also means that the moons of Uranus are probably bathed in radiation, albeit at levels much lower than those around Jupiter. This radiation could affect the surfaces of the moons, altering their chemistry and possibly creating environments that are hostile to organic molecules. But it could also drive chemical reactions that produce complex compounds, the kind of compounds that might be relevant to the origin of life. The reanalysis of the Voyager 2 data is a perfect example of how scientific understanding evolves. The original interpretation was not wrong. It was based on the best available data at the time. But as new analytical techniques are developed, as our understanding of solar system processes improves, and as we gain the ability to place old data in new contexts, our picture of Uranus changes. The Voyager 2 flyby was a snapshot, a single moment in time. What we are learning now is that Uranus is not a static world frozen in that moment. It is a dynamic, changing system, and we have only just begun to appreciate its complexity. The moons of Uranus, revealed in exquisite detail by Voyager 2, have become subjects of intense study in their own right. 5 large moons, Miranda, Ariel, Umbriel, Titania, and Obero, dominate the system, but they are accompanied by at least 24 smaller satellites, bringing the total to 29 as of 2025. Each of these moons has its own story to tell, its own geological history, its own potential for harboring secrets beneath its icy surface. Miranda, the innermost of the large moons, is perhaps the most remarkable. Its surface is a patchwork of radically different terrains, some heavily cratered and ancient, others smooth and young, still others marked by enormous canyons and ridges that suggest episodes of intense tectonic activity. The most prominent feature of Miranda is a set of 3 large structures known as coronae, which are roughly oval in shape and marked by concentric grooves and ridges. These coronae have no exact analogue elsewhere in the solar system, though they resemble some features on Jupiter's moon Europa and Saturn's moon Enceladus. Scientists believe they may be regions where warm ice from the interior rose toward the surface, causing the overlying crust to fracture and deform. The implication is that Miranda was once much more geologically active than it is today, possibly heated by tidal forces from Uranus or by radioactive decay in its interior. Ariel, the second innermost of the large moons, shows evidence of even more extensive geological activity. Its surface is crisscrossed by vast canyon systems, some of which are hundreds of kilometers long and several kilometers deep. These canyons appear to have been formed by extensional tectonics, the pulling apart of the icy crust as the moon's interior expanded, possibly due to the freezing of an internal ocean. Ariel also displays smooth plains that are relatively free of impact craters, suggesting they formed recently in geological terms. These plains may be the result of cryovolcanism, the eruption of liquid water and ammonia from the interior, which would have flooded low-lying areas and then frozen solid. Umbriel presents a stark contrast to its more active siblings. Its surface is uniformly dark and heavily cratered, with no obvious signs of recent geological activity. The largest feature on Umbriel is a bright ring on its surface, known as a crater, which may be an impact feature or a deposit of fresh ice from an internal source. The darkness of Umbriel's surface is puzzling. It reflects only about 16% of the sunlight that strikes it, making it one of the darkest moons in the solar system. This darkness may be due to the accumulation of dark material from the rings of Uranus, or it may be the result of radiation darkening of surface ices over billions of years. Titania and Oberon, the two largest moons of Uranus, are similar in size and composition, but they show different geological histories. Titania has a surface that is a mixture of ancient cratered terrain and younger plains, with a vast canyon system that extends for more than 1,000 kilometers. This canyon, known as Messina Chasma, is evidence of extensional tectonics on a global scale. Oberon, by contrast, is more heavily cratered, suggesting an older surface, but it also shows signs of geological activity, including a mountain that rises 6 kilometers above the surrounding terrain and may be a volcanic construct. In recent years, studies have suggested that these moons may have even more to offer than their spectacular surfaces. Computer modeling published in 2025 indicates that at least some of the Uranian moons may have liquid water oceans beneath their icy crusts, oceans that are kept warm by tidal heating and by the decay of radioactive elements in their rocky cores. If these oceans exist, they would join the growing list of subsurface oceans in the outer solar system, oceans on Europa, Enceladus, Ganymede, Callisto, and Titan that are considered among the most promising places to search for extraterrestrial life. The Uranian moons would be particularly interesting because they are so far from the Sun, receiving only about 1/400th of the sunlight that reaches Earth. Life in these oceans, if it exists, would have to be adapted to eternal darkness, deriving energy not from photosynthesis but from chemical reactions at hydrothermal vents or in the water itself. The discovery of subsurface oceans on the Uranian moons would transform them from objects of geological interest into targets of astrobiological significance. It would make a return mission to Uranus not just a planetary science priority, but a search for life priority, elevating the stakes and increasing the urgency of exploration. But for now, the oceans remain hypothetical, inferred from models rather than detected directly. Only a spacecraft in orbit around Uranus, with instruments capable of measuring the moon's magnetic fields and gravitational fields, could confirm their existence and characterize their properties. The discovery of new moons around Uranus continues to this day. In 2023, astronomers using the Las Campanas Observatory in Chile announced the discovery of a new moon temporarily designated S/LAS 2023 U1. It is tiny, only about 8 kilometers in diameter, and it orbits Uranus at a distance of several million kilometers, taking several years to complete one orbit. In February 2025, the James Webb Space Telescope, using its powerful NICAM instrument, discovered another moon, designated S-LAS 2025 U1. This moon is even smaller, perhaps only 4 or 5 kilometers across, and its discovery demonstrates the power of modern telescopes to detect objects that would have been invisible to previous generations of instruments. Each new discovery adds to our understanding of the Uranian system, revealing the complex interplay of gravitational forces that shaped the orbits of these tiny worlds over billions of years. The naming of these moons follows a tradition that began shortly after Herschel's discovery of the planet. The first 4 moons discovered, Titania and Oberon, found by Herschel himself in 1787, and Ariel and Umbriel, found by William Herschel in 1851, were named after characters from English literature. This tradition continued with the discovery of Miranda by Gerard Kuiper in 1948, and it has been maintained ever since. All of Uranus's moons are named after characters from the works of William Shakespeare and Alexander Pope, giving the Uranian system a literary flavor that is unique in the solar system. There is Ophelia and Desdemona, Juliet and Portia, Rosalind and Cressida, all orbiting the 7th planet in a celestial tribute to the greatest writers in the English language. The newest moons await their official names, and the astronomical community will eventually choose names that continue this tradition, adding new characters from Shakespeare or Pope to the growing list. The rings of Uranus, discovered by accident in 1977, remain among the most enigmatic features of the Uranian system. Unlike the bright icy rings of Saturn, which are composed of particles that reflect most of the sunlight that strikes them, the Uranian rings are dark, reflecting less than 2% of incident light. They are made of the darkest material in the solar system, material whose composition remains unknown. Spectroscopic analysis suggests that the ring particles may be composed of water ice mixed with dark organic compounds, or perhaps methane ice that has been darkened by radiation over billions of years. The rings are narrow, typically only a few kilometers to about 100 kilometers wide, and they are separated by gaps that are largely empty of material. 13 distinct rings have been identified, designated by Greek letters and numbers in order of discovery. The rings are aligned with Uranus's tilted rotational axis, meaning that as the planet orbits the Sun, the rings present changing orientations to Earth-based observers. When Voyager 2 approached Uranus in 1986, the rings appeared almost like a bullseye, concentric circles centered on the planet. As the spacecraft passed through the system and looked back, the rings appeared as a thin line, edge-on, and nearly invisible. This changing perspective is unique among ring systems, and it provides opportunities for observation that do not exist elsewhere. One of the great mysteries of the Uranian rings is how they remain so narrow. In the absence of some confining mechanism, ring particles would naturally spread out over time, evolving from a narrow ring into a broad, diffuse disk. The rings of Saturn, for example, are broad and complex because they lack efficient confining mechanisms. The rings of Uranus, by contrast, are razor-sharp, with edges that are defined to within a few kilometers. The most likely explanation is that shepherd moons are at work. Small satellites that orbit within or near the rings and use their gravity to confine the ring particles. Several such moons have been discovered, including Cordelia and Ophelia, which flank the brightest ring, Epsilon, and appear to keep it in place. But for many of the rings, no shepherd moons have been found, and the confining mechanism remains unknown. Possibly there are moons too small to detect from Earth, waiting to be discovered by a future orbiter. The rings are also young, at least by solar system standards. Dynamical calculations suggest that they cannot be more than about 600 million years old, and they may be even younger. This means that the rings formed long after Uranus itself, at a time when life on Earth was already diversifying in the oceans. The most likely formation scenario involves the breakup of a small moon, perhaps only a few tens of kilometers in diameter, that was shattered by a collision with a comet or asteroid. The debris from this collision would have gone into orbit around Uranus, gradually spreading out to form the rings we see today. If this scenario is correct, then the rings are transient features destined to disappear over the next few 100 million years as their particles spiral into the planet or are swept up by moons. We are fortunate to be living at a time when the rings exist, to have the opportunity to study them before they vanish into the darkness from which they came. In April 2025, a rare stellar occultation provided an unprecedented opportunity to study the rings in detail. Uranus passed directly in front of a star about 400 light-years from Earth, and astronomers around the world coordinated their observations to capture the event. It was the largest campaign ever organized to observe Uranus, involving more than 30 astronomers using 18 observatories on 5 continents. For about an hour, they watched as the star's light flickered and dimmed, blocked first by the rings and then by the planet itself. The precision of the timing measurements, accurate to within a few thousandths of a second, allowed scientists to determine the positions of the rings with extraordinary accuracy. They also measured the structure of the rings in unprecedented detail, revealing variations in density and thickness that had never been seen before. Perhaps most importantly, the occultation allowed scientists to refine Uranus's orbit, updating its position by about 400 kilometers. This may not sound like much, but for a spacecraft traveling billions of kilometers through space, 400 kilometers is a significant error. The new orbital data will be critical for planning any future mission to Uranus, ensuring that a spacecraft arrives at exactly the right place at exactly the right time. The occultation campaign of 2025 is just the beginning. Over the next decade, Uranus will pass in front of the galactic center of the Milky Way, providing even more opportunities for occultation studies. The best conditions will occur in 2031, when Uranus will be perfectly positioned for a series of occultations that could reveal details of its rings and atmosphere that are impossible to obtain by any other means. Astronomers are already planning for these events, coordinating their efforts to ensure that every occultation is observed by as many telescopes as possible. It is a global scientific effort, a testament to the enduring fascination that Uranus holds for those who study it. The atmosphere of Uranus, so calm and featureless when Voyager 2 flew past in 1986, has revealed itself to be a place of surprising complexity and dynamism. The basic composition is similar to that of Jupiter and Saturn, mostly hydrogen and helium, but with a crucial difference: the presence of about 2% methane. Methane absorbs red light efficiently, which is why Uranus appears blue-green to our eyes. The red component of sunlight is absorbed as it passes through the atmosphere, while the blue and green components are reflected back to space. But the atmosphere is more than just a passive filter of sunlight. It is a dynamic system of winds, clouds, and hazes that change with the seasons and respond to forces both internal and external. The temperature structure of the Uranian atmosphere is complex and poorly understood. At the cloud tops, the temperature is a frigid -224 degrees Celsius, the coldest of any planetary atmosphere in the solar system. But as one descends into the atmosphere, the temperature rises, reaching thousands of degrees at depth. This temperature gradient drives atmospheric circulation, but the details of that circulation remain obscure. One of the most surprising findings from recent observations is that the atmosphere of Uranus is not uniformly cold. The upper atmosphere, the thermosphere, is actually much hotter than it should be, reaching temperatures of several hundred degrees Celsius. This is paradoxical because the thermosphere is far from the planet's internal heat and receives only weak sunlight. Something must be heating it from above, and the leading candidate is the solar wind. A team at Imperial College London found that Uranus is the only planet in the solar system whose thermosphere appears to be heated by the solar wind, the stream of charged particles flowing constantly from the Sun. As the solar wind interacts with Uranus's magnetic field, it deposits energy in the upper atmosphere, causing it to heat up. This heating has been decreasing since 1990 as the solar wind's pressure has declined, and Uranus's thermosphere has cooled in response. The correlation is striking, and it provides strong evidence that the solar wind is indeed the heat source. The clouds of Uranus are made primarily of methane ice, which condenses at temperatures and pressures that occur in the upper atmosphere. These clouds are generally faint and difficult to observe, but occasionally they brighten dramatically, forming the storms that have been observed by Hubble and Keck. The storms appear to be seasonal, becoming more frequent and intense as Uranus approaches equinox. During the equinox periods, when the Sun is directly over the equator, the atmosphere receives more uniform heating than at other times, and this may trigger convective activity that brings methane-rich air from depth to the surface. The result is bright cloud features that can persist for months and sometimes evolve into complex systems that span thousands of kilometers. The winds of Uranus blow in the direction of the planet's rotation eastward at most latitudes, with speeds reaching up to 500 miles per hour. These winds are among the fastest in the solar system, comparable to the winds on Neptune, but much faster than those on Jupiter or Saturn. The wind speeds vary with latitude, with the fastest winds occurring at mid-latitudes and slower winds near the equator and poles. This pattern is similar to that on Jupiter and Saturn, suggesting a common mechanism for driving atmospheric circulation on all the giant planets. But there is a crucial difference. On Jupiter and Saturn, the winds are driven primarily by internal heat, by the slow release of energy left over from the planet's formation. On Uranus, internal heat is minimal, so the winds must be driven primarily by sunlight. This makes Uranus a unique laboratory for studying atmospheric dynamics, a place where we can see how a planetary atmosphere behaves when the primary energy source is external rather than internal. The haze layers of Uranus are another fascinating feature. Above the main cloud deck, there are layers of photochemical haze, produced when sunlight breaks apart methane molecules, and the fragments recombine to form more complex hydrocarbons. These haze layers are thin and tenuous, but they play an important role in the planet's energy balance, absorbing sunlight and heating the upper atmosphere. The haze layers also vary with the seasons, becoming thicker over the summer pole as the long polar day allows photochemical reactions to proceed continuously for decades. Observations by Hubble over a 20-year period have documented this seasonal variation, showing how the North Pole has become progressively brighter as Uranus moves towards summer solstice, which will occur in 2030. By that time, the North Pole will be pointing almost directly at the Sun, and the haze layers there will be at their thickest. Then, as Uranus moves into northern autumn, the haze will gradually dissipate, and the South Pole will begin its long polar day, accumulating its own haze layers over the following decades. This seasonal cycle is unique in the solar system, and it offers a window into the complex interactions between sunlight, atmospheric chemistry, and circulation that shape the climates of all planets. The interior of Uranus remains largely mysterious, hidden beneath layers of atmosphere and cloud that no spacecraft has ever penetrated. But scientists have developed models of the interior based on the planet's mass, radius, rotation rate, and gravitational field. And these models paint a picture of a world that is fundamentally different from either the rocky terrestrial planets or the gas giants Jupiter and Saturn. The standard model of Uranus's interior, developed after the Voyager 2 flyby and refined over subsequent decades, posits a layered structure. At the center, there is a rocky core, perhaps 10 to 15% of the planet's mass, composed of silicate minerals and iron. Surrounding this core is a thick mantle of icy materials, water, ammonia, and methane, compressed by immense pressure into a state that is neither solid nor liquid, but something in between, often described as superionic. Above the mantle is a gaseous envelope, mostly hydrogen and helium, that extends to the cloud tops we see from space. The boundary between the mantle and the envelope is not sharp. There is a gradual transition from the dense, fluid-like material of the mantle to the thinner, more gas-like material of the envelope. This layered structure is similar to that of Neptune, which is why the two planets are grouped together as ice giants. But recent modeling has challenged this simple picture. In 2025, a study published in the journal Astronomy and Astrophysics by Luca Morf and Ravit Held of the University of Zurich took an agnostic approach to modeling Uranus's interior. Rather than assuming a particular composition, they generated millions of random models and then compared them to the observational data, gravitational field, rotation rate, and so on, to see which ones were consistent with what we know. The results were surprising. The possible compositions of Uranus span an enormous range. In some models, the planet is almost entirely water, with only a tiny fraction of rock. In others, it is predominantly rock, with water making up only a small percentage. Between these extremes, there is a continuum of possibilities, each consistent with the available data. This means that Uranus could be a rock giant rather than an ice giant, a world whose interior is dominated by silicate minerals rather than water and ammonia. If that is the case, then our understanding of how Uranus formed would need to be revised. The standard model of planet formation holds that ice giants form in the outer solar system, where temperatures are low enough for water and other volatiles to condense into solid particles that can accumulate into planets. If Uranus is predominantly rock, it must have formed much closer to the Sun, where rocky materials were abundant, and then migrated outward to its current position. Such migration is possible, indeed it is thought to be common in planetary systems, but it would have profound implications for the history of the solar system. The morph and held study is theoretical, based on models rather than direct observations. The only way to determine the true composition of Uranus's interior is to send a spacecraft that can measure the planet's gravitational field with high precision, allowing scientists to infer the distribution of mass within. Such measurements are a key objective of proposed missions to Uranus, and they would finally resolve the question of whether Uranus is an ice giant, a rock giant, or something in between. But even without new data, the theoretical work is valuable because it highlights the depth of our ignorance. We have known about Uranus for more than 2 centuries. We have flown a spacecraft past it. We have observed it with the most powerful telescopes ever built, and yet we still do not know what it is made of. This is a humbling realization, and it underscores the importance of returning to this distant world. One of the most captivating ideas about Uranus's interior is the possibility of diamond rain. The conditions in the mantle, immense pressure and high temperature, are such that methane molecules, composed of 1 carbon atom and 4 hydrogen atoms, can be broken apart. The carbon atoms are then compressed into diamond crystals, which rain downward through the mantle toward the core. This process has been simulated in laboratories using high-powered lasers, and it appears to be plausible under the conditions that exist in Uranus's interior. If diamond rain does occur on Uranus, it would be a phenomenon unlike anything on Earth. Diamonds would form not as rare gems, but as common precipitation, falling continuously through the planet's interior. They would start as tiny crystals, perhaps only a few atoms across, but as they fell, they would grow, accreting more carbon from the surrounding material. By the time they reached the core, they might be enormous, perhaps kilograms or even tons in mass. The core itself might be encrusted with a layer of diamond, a diamond shell surrounding the rocky interior. This idea is captivating, but it is also speculative. The conditions in Uranus's interior are difficult to replicate in the laboratory, and the simulations that suggest diamond rain are based on approximations that may not capture all the complexities of the real situation. Moreover, the new modeling by Morph and Held suggests that Uranus might not have enough methane to produce significant diamond rain. If the planet is predominantly rock, with only a small fraction of icy materials, then methane would be scarce and diamond formation would be limited. On the other hand, if Uranus is predominantly water, methane could be abundant and diamond rain might be a major process. Again, we cannot know without new data. The question of diamond rain on Uranus is more than just a curiosity. It has implications for the planet's internal structure and evolution. If diamonds are forming and falling, they would carry heat with them, contributing to the planet's internal energy budget. They might also affect the planet's magnetic field, if diamonds are electrically conductive under the extreme conditions of the interior. Understanding whether diamond rain actually occurs on Uranus would tell us something fundamental about the conditions inside the planet and about the processes that shape its evolution over billions of years. The idea of diamond rain also captures the public imagination in a way that more prosaic scientific questions do not. It is a reminder that the universe is stranger and more wonderful than we can easily imagine, that places exist where the ordinary rules of everyday experience do not apply, where diamonds fall from the sky and oceans are made not of water but of superionic fluids that conduct electricity like metals. This sense of wonder is part of what drives planetary exploration, the desire to see with our own eyes what we can only imagine with our minds. The possibility of life on or around Uranus is a question that has gained increasing attention in recent years. At first glance, the Uranian system seems an unlikely place for life. The planet itself has no surface. Its atmosphere is cold and turbulent, and its upper layers are bathed in radiation from space. But the moons are another matter. If, as recent modeling suggests, some of the large moons have subsurface oceans, then those oceans could be habitats for life. The conditions in such oceans would be extreme by Earth standards, cold, dark, under immense pressure, but they would not be impossible. On Earth, life has been found in the most unlikely places, in deep ocean hydrothermal vents, where temperatures exceed 400 degrees Celsius. Subglacial lakes in Antarctica that have been isolated from the surface for millions of years. In rocks kilometres below the surface, where the only energy source is chemical rather than solar. If life can exist in those places, it might exist in the oceans of Uranus's moons. The energy source for such life would not be sunlight, which cannot penetrate through kilometers of ice, but chemical energy from hydrothermal vents or from reactions between water and rock. The basic ingredients for life as we know it, carbon, hydrogen, oxygen, nitrogen, sulfur, phosphorus, are all present in the Uranian system. The moons are made of water, ice, and rocky material, so carbon and other elements would be available if they can be mobilized into the ocean. The biggest unknown is time. Life takes time to originate and evolve, and we do not know how long the subsurface oceans of Uranus's moons have existed. If they are relatively young, perhaps formed by tidal heating that has since diminished, then life might not have had time to get started. If they are ancient, stable over billions of years, then the possibility of life becomes more plausible. The search for life on the Uranian moons would be challenging. Any ocean is buried beneath kilometers of ice, and accessing it would require technology far beyond anything we currently possess. But we do not need to access the ocean directly to look for signs of life. A spacecraft in orbit around Uranus could study the moons in detail, measuring their magnetic fields to confirm the presence of subsurface oceans, analyzing their surfaces for organic compounds, and looking for plumes of water vapor like those that erupt from Enceladus. If plumes exist, a spacecraft could fly through them and sample their contents, searching for the chemical signatures of life. This is exactly what the Cassini spacecraft did at Enceladus, flying through plumes of water vapor and detecting organic molecules that hint at the possibility of life in that moon's subsurface ocean. A similar mission to Uranus could do the same, searching for signs of life in the plumes of Ariel or Miranda if they exist. The astrobiological potential of the Uranian system is one of the strongest arguments for a return mission. The discovery of life elsewhere in the solar system would be one of the most profound events in human history, transforming our understanding of our place in the universe and raising questions that we cannot yet imagine. Even if no life is found, the study of the Uranian moons would tell us about the conditions under which life might arise, and about the prevalence of habitable environments in the solar system and beyond. The path to a return mission to Uranus has been long and winding. In the decades following the Voyager 2 flyby, various mission concepts were proposed, but none advanced beyond the study phase. The distances involved are immense, the travel times long, the costs high, and there were always other priorities, other planets that seemed more urgent or more accessible. But in recent years, the scientific case for a Uranus mission has grown steadily stronger. The discoveries from Earth-based telescopes, the theoretical advances in understanding planetary formation and evolution, and the recognition of the astrobiological potential of the Uranian moons have all contributed to a sense that Uranus can no longer be ignored. In 2022, the National Academies of Sciences, Engineering and Medicine released the latest Planetary Science Decadal Survey, a once-in-a-decade report that sets priorities for NASA's planetary science program. The report was unambiguous. The highest priority for a new flagship mission, it declared, is a Uranus orbiter and probe. This recommendation carries enormous weight. It means that the scientific community has spoken, that the case for Uranus has been made, and that NASA should move forward with planning such a mission. The proposed mission would consist of two elements: an orbiter that would spend years studying the Uranian system from orbit, and a probe that would descend into Uranus's atmosphere, measuring its composition, temperature, and pressure as it falls. The orbiter would carry a suite of instruments: cameras to image the planet and its moons, spectrometers to analyze their compositions, magnetometers to study the magnetic field, and radio science experiments to measure the gravitational field and probe the interior structure. It would spend perhaps 5 years in orbit around Uranus, observing the planet through a substantial portion of its seasons and making multiple flybys of the major moons. The probe would be even more ambitious. It would enter Uranus's atmosphere at tremendous speed, deployed from the orbiter months before arrival. As it descended by parachute through the clouds, it would measure atmospheric composition, searching for noble gases and their isotopes, which hold clues to the planet's formation. It would measure temperature and pressure at different depths, revealing the structure of the atmosphere, and it would continue sending data until it was crushed by the increasing pressure, perhaps an hour or two after entry. The combination of orbiter and probe would revolutionize our understanding of Uranus. We would finally learn what the planet is made of, how its interior is structured, how its magnetic field is generated, how its atmosphere works, what its rings are composed of, and whether its moons harbor subsurface oceans. It would be the most ambitious mission to the outer solar system since Cassini, and it would set the stage for even more ambitious missions in the future, perhaps landers on the moons or sample return missions. The timing for such a mission is critical. Because of the alignment of the planets, there are optimal launch windows for a Uranus mission in the early 2030s. A spacecraft launched during these windows could use a gravity assist from Jupiter to shorten the journey by several years, arriving at Uranus in the early 2040s. If the launch window is missed, the next opportunity would not come for more than a decade, delaying arrival until the 2050s. The urgency is real. If we want to explore Uranus in our lifetimes, we need to act now. The Chinese National Space Administration has also proposed a mission to Uranus, Tianwen 4, which would launch in the 2030s and include both an orbiter and a lander. This mission is still in the early planning stages, but it demonstrates that Uranus is becoming a focus of international interest. If both NASA and CNSA proceed with missions, we could have 2 spacecraft exploring the Uranus system simultaneously, providing complementary perspectives and increasing the scientific return. The next decade will be critical. Mission concepts will be refined, technologies will be developed, and political support will be mobilized. Whether we ultimately send a mission to Uranus will depend on factors beyond science, on budgets, on priorities, on the whims of governments. But the scientific case has never been stronger, and the opportunity has never been more clear. We stand at a threshold. On the other side lies a new era of exploration, an era in which the seventh planet finally receives the attention it deserves. Whether we cross that threshold is up to us. As we contemplate the future of Uranus exploration, it is worth reflecting on what we have learned in the 4 decades since Voyager 2's fleeting encounter. We have learned that Uranus is not the static, featureless world it appeared to be in 1986. It is a place of dramatic seasonal change, of massive storms that can dominate an entire hemisphere, of winds that race at hundreds of miles per hour. We have learned that its magnetic field is even stranger than we thought, shaped by processes that may date back to a cataclysmic collision billions of years ago. We have learned that its rings are young and dark, made of material that reflects almost no light, and that they are confined by mechanisms we do not fully understand. We have learned that its moons are diverse and complex, with surfaces that record violent geological histories and interiors that may harbour liquid water oceans. We have learned that Uranus itself may not be an ice giant at all, but a rock giant, a world whose composition challenges our models of planet formation. And we have learned that the Voyager 2 flyby, for all its scientific riches, was just a snapshot, a single moment in the life of a dynamic and changing system. The Uranus we saw in 1986 was not the Uranus of today, and it will not be the Uranus of tomorrow. As the planet continues its slow 84-year orbit around the Sun, it will continue to change, its seasons advancing, its storms waxing and waning, its atmosphere evolving in ways we can only dimly imagine. The next few decades will be particularly interesting. Uranus is approaching its northern summer solstice, which will occur in 2030. At that time, the North Pole will be pointing almost directly at the Sun, and the Northern Hemisphere will experience continuous daylight for the first time in 42 years. The atmospheric circulation will adjust to this new regime, and we can expect dramatic changes in cloud cover, wind patterns, and storm activity. Telescopes on and around Earth will be watching, documenting these changes as they occur. And if a spacecraft is on its way, it will arrive just in time to witness the aftermath, to see how the Uranian system responds to the changing seasons. The occultation campaigns of the next decade will provide unprecedented data on Uranus's rings and atmosphere, refining our knowledge and helping to plan the trajectory of any future mission. The James Webb Space Telescope and its successors will continue to observe Uranus, peering deeper into its atmosphere than ever before, and revealing details that have remained hidden since the planet's discovery. And theoretical modelers will continue to refine their simulations, exploring the range of possibilities for Uranus's interior and evolution. But ultimately, there is no substitute for going there. Telescopes can tell us a great deal, but they cannot measure the gravitational field with enough precision to reveal the interior structure. They cannot sample the atmosphere to determine its composition. They cannot fly through plumes of water vapor to search for organic molecules. They cannot image the surfaces of the moons at the resolution needed to understand their geological history. For that, we need a spacecraft. We need an orbiter that can spend years in the Uranian system, patiently building up a picture of this distant world and its family of moons. We need a probe that can plunge into the atmosphere, measuring what lies beneath the clouds. We need the kind of sustained, systematic exploration that only a dedicated mission can provide. The technology exists. We have built spacecraft that have explored Jupiter, Saturn, and their moons in exquisite detail. We have sent probes into the atmosphere of Jupiter and landed on Titan. We have flown by comets and asteroids, returned samples from the solar wind, and placed rovers on Mars. A mission to Uranus is well within our capabilities. The question is not whether we can do it, but whether we will. Will we make the investment, take the risk, commit the resources? Will we decide that understanding this distant world is worth the cost? The scientific community has spoken clearly. The Planetary Science Decadal Survey has made Uranus the top priority. The launch window is opening. The opportunity is now. As we stand on the threshold of a new era of exploration, it is worth remembering why we explore in the first place. We explore because we are curious. We explore because we want to understand our place in the universe. We explore because the unknown calls to us, because there are questions that demand answers, because we are the kind of creatures who look at the night sky and wonder what is out there. Uranus is out there, waiting. It has been waiting for billions of years, rolling around the sun on its side, its secret interior hidden beneath layers of cloud, its strange magnetic field carving out a bubble in the solar wind, its family of moons orbiting in the darkness. It has been waiting for us to come and see it, to learn its story, to add its chapter to the great book of human knowledge. The Voyager 2 flyby was just a glimpse, a tantalizing hint of what lies beyond. Now it is time to go back. It is time to give Uranus the attention it deserves. It is time to answer the questions that have accumulated over 4 decades of study and to discover new questions we have not yet imagined. The next decade will determine whether we seize this opportunity or let it slip away. The choice is ours. In the end, the story of Uranus is the story of human curiosity and human limitation. It is the story of how a musician with a homemade telescope expanded the known boundaries of the solar system, and how a robotic spacecraft, launched when many of us were not yet born, gave us our only close-up look at this distant world. It is the story of how patient observation with telescopes on and around Earth has gradually revealed the dynamic nature of a planet we once thought was static, and how theoretical modeling has opened up possibilities we never considered. It is the story of how a planet that began as a punchline has become a scientific priority, a world whose mysteries have captivated a new generation of researchers. And it is the story of how we stand at a moment of decision, a moment when the path forward is clear, the technology is ready, and the scientific case is unassailable. Whether we take that path will say something about us, about our species, about our values and our priorities. Do we have the will to reach out into the darkness and embrace the unknown? Do we have the patience to wait decades for answers? Do we have the wisdom to invest in knowledge that may not pay immediate dividends, but will enrich our understanding of the universe for generations to come? These are not scientific questions. They are human questions, and they have no easy answers. But as we ponder them, we can take comfort in what we have already achieved. We have found Uranus. We have named its moons after characters from Shakespeare. We have measured its winds and its temperature and its magnetic field. We have discovered its rings and watched its storms. We have built a body of knowledge that would have seemed like magic to William Herschel standing in his garden in Bath on that March night in 1781. And we have done it all without ever setting foot on its surface, without ever breathing its air, without ever feeling the faint sunlight that reaches its cloud tops. We have done it with our minds, with our instruments, with our insatiable curiosity. That is who we are. That is what we do. And if we can do all that without ever going there, imagine what we could do if we actually went. Imagine an orbiter circling Uranus for years, sending back images of storms and clouds and rings in exquisite detail. Imagine a probe descending through the atmosphere, measuring the composition of the clouds, the temperature at different depths, the pressure that would crush any human-made object within hours. Imagine flybys of Miranda, Ariel, Umbriel, Titania, and Oberon, revealing their surfaces in unprecedented resolution, showing us the details of their canyons and craters and smooth plains, perhaps even detecting plumes of water vapor erupting from subsurface oceans. Imagine the data, the discoveries, the revelations. Imagine the questions that would be answered and the new questions that would arise. That future is within reach. It is not guaranteed, but it is possible. And the decisions we make in the next few years will determine whether that future becomes reality or remains a dream. The launch window is opening. The scientific community is ready. The technology exists. All that remains is for us to decide that Uranus matters, that understanding this distant world is worth the investment of time and money and effort. All that remains is for us to choose exploration over complacency, curiosity over indifference, wonder over apathy. It is a choice we have made before, for Mars, for Jupiter, for Saturn. Now it is time to make it for Uranus. The seventh planet awaits, and as the sun sets on another day, as the stars emerge in the darkening sky, we can look toward the constellation of Aries, where Uranus currently resides, and know that out there, nearly 3 billion kilometers away, a world is turning on its side, its long polar night giving way to dawn, its clouds swirling in patterns we have only begun to understand, its mysteries waiting to be revealed. Good night, Uranus. Good night, and sleep well, for when you wake, you may find visitors from Earth, come at last to learn your secrets, to write your story, to add your voice to the chorus of worlds that humanity has come to know. Until then, we watch and we wait and we wonder, and we dream of the day when we will finally return. The story of Uranus is not just the story of a planet. It is the story of human knowledge, of how we come to understand the universe one discovery at a time. It is the story of how a single encounter lasting only a few hours can form the foundation of decades of research. It is the story of how old data, re-examined with new eyes, can yield new insights. It is the story of how telescopes, growing more powerful with each passing year, can reveal details that were invisible to their predecessors. It is the story of how theoretical models running on increasingly powerful computers can explore possibilities that no spacecraft has yet tested. And it is the story of how a scientific community, working across generations and across continents, can gradually piece together a portrait of a world they have never visited. That portrait is far from complete. There are gaps in our knowledge, questions we cannot answer, mysteries that remain unsolved. But it is a start. It is a foundation upon which future discoveries can be built. And as we look toward the future, as we contemplate the missions that may soon depart for this distant world, we can take pride in what we have already accomplished. We have done much with little. We have learned much from a single flyby. Imagine what we could do with an orbiter. Imagine what we could learn with a probe. Imagine how our understanding would expand if we could spend years in the Uranian system, studying it from every angle, at every season, through every change. That is the promise of a return mission. That is the future that awaits if we have the courage to pursue it. The scientific case is clear. The technology is ready. The opportunity is now. All that remains is for us to act. And so we come to the end of this journey through the Uranian system, this exploration of a world that has been called the butt of jokes and the forgotten planet. We have seen that Uranus is anything but forgettable. It is a world of extremes, of violent history and serene beauty, of profound mysteries and tantalizing possibilities. It is a world that challenges our assumptions and expands our imagination. It is a world that deserves our attention, our curiosity, our respect. As we turn away from Uranus and back toward Earth, back toward the familiar comforts of our home planet, let us carry with us the sense of wonder that this distant world inspires. Let us remember that the universe is full of strange and wonderful places, places we have only begun to explore. Let us remember that the questions we have answered are far fewer than the questions that remain. And let us look forward to the day when we will return to Uranus, when we will finally learn its secrets, when we will add its story to the great tapestry of human knowledge. Until that day, we watch and we wait, and we wonder and we dream of the future. Good night, Uranus. Good night and farewell.